A very good morning to all of you, and I welcome you all with greetings of the day. Well, today is Wednesday, 4th of January 2023, and I'm going to deliver fourth lecture on course on electric drives. So this is lecture number 4. In today's lecture, I'm going to continue with dynamics of electric drives. In fact, first of all, I am going to discuss with you equivalent drive parameters. I write here equivalent drive parameters. Well, in equivalent drive parameters, we will try to find out what is the total moment of inertia and what is the total torque required by the load and how much torque the motor has to develop in order to put the load into motion. Okay, now we may have two different types of loads. One may be a rotational type load which rotates, and another may be a translational load in which the load performs a linear motion rather than a rotatory motion. So first of all, I will take case A. Case A is for rotational load. I will write here rotational load. Okay, now this is our motor. Maybe an AC motor if the drive is AC drive, or it may be a DC motor if the drive is a DC drive. This is the transmission equipment or coupling between motor and load. This is the mechanical load. Let us assume we have two loads. This is load number 0, and then we have second load, load 1, which is coupled with this system via gear system. This is the gear. These are the teeth which are on the motor side, teeth of the gear, and these are the teeth of the gear on the load side. And load is coupled to the gear here. This is mechanical load 1. Let us assume the moment of inertia of this motor and load, total moment of inertia is J0, and moment of inertia of this system is J1. Okay. Let us assume that the motor develops a torque, electromagnetic torque T, which puts the motor and its driven load into rotation, and the load runs at a speed of omega m. So what is the opposing torque of the load, or in other words, what's the load torque? Let's call that TL0. TL0 is the load torque of load 0. And let us suppose this load 1 also rotates because of this arrangement. It rotates at a speed of omega m1. And let us suppose the load torque here is TL1. Here the load torque is TL0. Here the load torque is TL1. N is the number of teeth of the gear on the motor side, and N1 is the number of teeth of the gear on the load side. Okay. So this load is directly coupled with the motor via this shaft. There is no gear arrangement. However, load number 1 is coupled to the motor via this gearing arrangement. We have a ratio which is called gear ratio. I will write here gear ratio. It is represented by A, and it is given by N divided by N1. And in terms of speed, it is omega m1 by omega m. Okay, where omega m1 is the speed at which load 1 rotates, and omega m is the speed at which load 0 rotates or load O rotates. N is the number of teeth on the motor side, and N1 is the number of teeth of the gear on the load side. Okay, so you can very clearly see that the speed of this load omega m1 is inversely proportional to number of teeth N1. Similarly, omega m is inversely proportional to number of teeth N. Okay, fine. So we can say that omega m is inversely proportional to the number of teeth of the gear. Now let us write an equation. First of all, we'll try to find what is the total moment of inertia. The moment of inertia motor and load 0 arrangement is J0, and moment of inertia of this system is J1. What is the total moment of inertia refer to the motor side, okay, because we have a gearing arrangement. The load 1 is not directly coupled with the motor, it is coupled via gear. So therefore, whatever is the moment of inertia here, through the gear arrangement, it will be reflected on this side and it will have a different value. How to find total moment of inertia of the load? Okay, so I will write here effective kinetic energy of the system. Effective kinetic energy of the system. When I say effective kinetic energy of the system, see, when the motor rotates, when the motor runs, it runs load naught at speed omega m, and it also runs load 1 at speed omega m1, okay, where omega m1 is different from omega m because of this gearing arrangement. When the whole system starts rotating, kinetic energy gets stored in the rotating parts of the motor and both the loads. And what is the effective kinetic energy of the system? Effective kinetic energy of the system is given by this relation, half of J into omega m square. Okay, J is the total moment of inertia of the whole system, which includes the moment of inertia of motor, load 0 and load 1. And the formula for kinetic energy is given by half of moment of inertia into speed square, half of J into omega m square. Now, if we split this kinetic energy, we split it into two parts. Number one, kinetic energy in this arrangement, motor and load arrangement, plus the kinetic energy stored in this arrangement, okay, in load 1. What is the kinetic energy stored in this system? It is given by half of what is the moment of inertia of this mechanism or this system, J naught. And what is the speed at which motor and load 0 runs? It is omega m. So it is half of J naught omega m square plus what is the kinetic energy stored in this load? It is half of what is the moment of inertia of this load, J1, and at what speed it is running, omega m1 square. Okay, so therefore total kinetic energy stored in the system is equal to kinetic energy stored in this system plus kinetic energy stored in this load, half of J0 omega m square plus half of J1 omega m1 square. This 1 by 2, it cancels on both sides. So from this you can find the effective moment of inertia or total moment of inertia of the system. It is given by J naught into omega m square. What will happen to this omega m square when it is transferred or shifted to right hand side? It will get divided. It will divide. Plus similarly I have J1 into omega m1 square divided by this omega m square. Right. So therefore, if I further simplify it, this omega m square goes. So J will be equal to J naught plus J1. This is omega m1 square by omega m square. This is omega m1 by omega m whole square. And by the way, what is the ratio of the speeds? What is the ratio of speed of this load and this load? Omega m1 by omega m. We have already defined that. That's the gear ratio, A. So therefore, J is equal to J naught plus A square J1. So therefore, total moment of inertia or total inertia referred to the motor side, okay, J is equal to J naught, which is the moment of inertia of motor and load 0, plus A square J1, which is the moment of inertia of load 1 referred to this side. Okay, when you refer it to this side, motor side, you have to multiply it by gear ratio square, A square. So J is equal to J naught plus A square J1. So this gives us total moment of inertia. Okay, before designing an electric drive system and selecting a motor for driving a set of loads, we must have knowledge of what is the total moment of inertia against which the motor has to be used, for which the motor has to be used, so that the motor develops the required amount of torque. Fine. After this, we'll try to find out the total torque developed, which is to be developed by motor to keep the system running. Okay. For that purpose, I will write here power seen by the motor, or power to be developed by motor. How much power motor has to develop? We know power equation is P is equal to omega into T. Power is speed into torque. So the power which is to be developed by motor is equal to omega m because omega m is the speed of the motor into torque. Torque is the TL. Let me write this as TL. TL is the total load torque or total torque which is to be developed by motor is equal to. Now this is equal to power which is required by load 0, okay, plus power which is required by load 1. What is the power required by load 0? It is running at same speed omega m, and what is the torque which is developed by, what is the load torque of load 0? It is TL naught plus how much is the torque, how much is the power required by load 1, okay, so that it runs at speed omega m1. Its speed is omega m1 into torque is TL1, and we have to divide it by eta, where what is eta, or let's call this eta 1, where eta 1 is called coupling efficiency or gear efficiency. Eta 1 is the gear efficiency. You have to divide this speed into torque developed by this load 1 divided by gear efficiency, eta 1. Okay. Now from this we can get TL. So TL, total load torque, okay, which is equal to load torque of load 0 plus load torque of load 1, and this is equal to TL naught into omega m divided by this omega m plus TL1 by eta 1 into omega m1 by this omega m, right? So therefore from this we can get the total load torque. So therefore total load torque which is to be developed by motor to keep both the loads running, TL is equal to omega m divided by omega m. So this is TL naught plus, what is omega m1 by omega? It is again a gear ratio A1. Let's call this gear ratio as A1 and multiplied by TL1 by eta 1. Okay, so this is the mathematical expression for total load torque which is seen by the motor. And when the motor, how do you select the motor? You select the motor on the basis of what is the total torque it has to develop, and total torque it has to develop is equal to TL naught plus A1 times TL1 by eta 1, where A1 times TL1 by eta 1 is the load torque of load 1 referred to this side, motor side. Okay, fine. So these are two very important equations for rotational load, and in general here I have considered two loads, but your motor may drive more than two loads. In case you have multiple loads driven by a motor, so in that case in general we will write the total moment of inertia J is equal to J naught plus A1 square J1 plus A2 square J2 plus so on. Okay, and similarly the total load torque which is to be developed by motor is equal to TL naught plus A1 into TL1 by eta 1 plus A2 into TL2 by eta 2 plus so on. This is the total load torque. Okay, so this this is how we calculate the total load torque and total inertia or total moment of inertia of motor and motor driving multiple number of loads through gearing mechanism. Okay, once you have the information about total inertia or total moment of inertia and total load torque, you can design, you can select the rating of the motor so that the motor is able to run the load against run the load which has a total moment of inertia given by this equation, and motor at least develops a torque which is equal to total load torque TL given by this equation. This helps us in the selection of motor of a particular rating. This is for rotational load. Let us quickly go for second type of load, which is translational load. I will write here case B is for translational load. The example of translational load, if you see the example of a translational load, is a lift. A lift is driven by motor. Motor basically produces the rotating motion, but that rotating motion is converted into or into linear motion. So, and the lift moves from say ground floor to some top floor and top floor to ground floor like this. So this is linear motion, this is not rotating motion. But motor produces the rotational motion. That rotational motion has to be converted into translational motion or linear motion. So example is a lift. Let us take such a system. This is motor again, maybe DC or AC motor, depending upon whether your drive is DC drive or AC drive. And let us suppose this is the load. The motor develops a torque T, which results in rotation at speed omega m, and the load torque is TL, or let's call this torque as TL naught. Okay. Then we have this mechanism. This converts rotational motion into linear motion. It's a mechanism which is there in the lifts. It converts rotational motion into linear motion. This is rotational to linear motion transmission. So what is the job of this block? The job of this block is to convert the rotational motion produced by motor into linear motion. Okay, and then it is coupled with the mass M. This is mass M. Okay, this is the lift container in which the load, say human beings are there, and we need to lift the human beings from one floor to another floor, bottom to top or top to bottom. And the force developed is F1, and the velocity at which the lift moves up or down is, let's call that velocity or speed as V1. The total moment of inertia of motor and this load is again J naught, right? So again, let us find the total moment of inertia of the system, which comprises of moment of inertia of motor and load J naught plus moment of inertia of this system, which this is the rotational system and this is the linear system or translational system. So I will again write effective kinetic energy of system. It is given by half of J omega m square is equal to half of kinetic energy of motor and load, this load 0. So this is half of J naught into omega m square because it is running at speed omega m, plus what is the kinetic energy of this system? It's not a rotational system now, it's a linear system, translational system. It moves up and down, it does not rotate. It has a linear motion, not rotational motion. It is given by half of mv square, half of mass into velocity square. Okay, so this 1 by 2 goes. So from this we can find J is equal to J naught times omega m square divided by this omega m square plus m v1 square by omega m square. So from this we can find the total moment of inertia of the system referred to the motor side. J is equal to J naught because they cancel, plus m times v1 by omega m whole square. So this is the total moment of inertia of a translational system or translational load. Okay. So what about the total torque which is to be developed by the motor, or total load torque, which comprises of load torque of load 0, which is a rotational load, plus the torque of let's call this load 1, which is not a rotational load, which is a linear or translational load. Okay, so power to be developed by motor, again P is equal to omega T, that is omega m into TL, where TL is the total load torque to be developed by motor, is equal to what is the power required by load naught to put this load 0 into rotation. It is omega m into TL naught, where omega m is the speed at which this load runs, plus multiplied by TL naught is its load torque, plus what is the power required by this. Now this is not a rotational load, this is a linear load or translational load, and its power is given by force F1 into velocity V1 by eta 1. Why, what is this eta 1? Eta 1 is called coupling efficiency. Coupling efficiency, because this linear load or translational load is coupled to the motor via this mechanism, and this mechanism has an efficiency of eta 1. Eta 1 is called the coupling efficiency. So from this we can find the total load torque TL equal to TL naught into omega m divided by omega m. This omega m will get divided, plus F1 by omega m into V1 by eta 1. So this will give total load torque. TL is equal to, so this goes, so this is TL naught plus F1 by eta 1 into V1 by omega m. So this is the total load torque. Okay. So once you know the load torque requirement of load 0 and the torque requirement of this mass linear load, which is given by F1 by eta 1 into V1 by omega m, you know what is the speed V1, you know what is this rotational motion omega m, you know how much is the force. You can calculate the force developed by this lift divided by coupling efficiency eta 1, and adding the two terms you will get total load torque requirement. And therefore you accordingly select a motor which can at least develop a torque which is greater than or equal to TL, total load torque, to put the lift or the load into motion. So this is about drive parameters. We have taken two different cases. In the first case we have taken rotational load, and second case was translational load, and for both types of loads we have tried to find what is the total moment of inertia, how we calculate total inertia, and how we calculate total torque requirement of the load. Fine. After this I am going to discuss with you components of load torque. Components of load torque. See, when I talk of load torque, you have a mechanical load. This mechanical load requires certain torque, okay, for put it into rotation or put it into motion, and that total load torque, I will write here, total load torque is given by this equation. It has different components. TL, it is given by T small l plus TF plus TF plus TW. Now what are these? Are the different components of load torque. What is this T small l? T small l is useful load torque. I mean, this is the torque which puts the load into rotation. This is the useful load torque. TF is called frictional torque or friction torque. Friction torque. And TW is called windage torque. These are the different components of load torque. Now, as far as this TF is concerned, this friction torque, I will write here, this friction torque also comprises of different components. Friction torque, TF, it is given by this equation, TS plus TV plus TC. What is this TS? TS is called static friction torque. Static friction torque, or it is also called stiction. It is the friction torque when the entire motor load system is at standstill, stationary. At that time, certain amount of friction torque is there, that's called static friction torque. It's also called stiction. Okay, what is TV? TV is called viscous friction torque. Viscous friction torque, and this TV is directly proportional to speed. As the speed increases, this viscous friction torque also increases. We can write viscous friction torque is equal to B into omega m, where what is B? B is called viscous friction coefficient. It is called viscous friction coefficient. Viscous friction coefficient. Okay. And what is the third component of friction torque? TC. TC is called Coulomb torque. Coulomb friction torque. Coulomb friction torque. and it is not dependent upon the speed, it is constant, it is always constant. So let me show different components of friction torque one by one on torque speed characteristic. So this is your friction torque, total friction torque TF. We know that total friction torque TF is equal to static friction torque TS plus viscous friction torque TV plus Coulomb torque TC, or it is equal to TS plus B omega m, because viscous friction torque is directly proportional to speed. So it is equal to B omega m, where B is the viscous friction coefficient, plus Coulomb torque, which is constant. This is friction torque, this is minus TF, this is speed omega m, and this is minus omega m. Now this viscous friction torque, first component is static torque. It is like this, it is given by this line here and by this line. This is TC, TS here and TS here. That means when the motor and the load is at standstill, there is a certain amount of torque which is called static friction torque, and it is this much. And when the system's load starts running, then this viscous friction torque starts falling, and at a particular value of the speed it becomes zero. But it is there only during the static conditions, when the system is at standstill. When the system is rotating above this speed, then it is absent. So it shows its presence only during the during the starting period, from no load up to from no load speed to a small amount of speed, okay, from zero speed to small speed, and then it disappears. Second type of torque is TV, viscous torque, which is viscous friction torque, which is directly proportional to speed. So it is like this. This is TV and this is TV minus TV. Okay, I am showing in first quadrant as well as in third quadrant. Now you can very clearly see that this TV is equal to B omega m. It is directly proportional to omega m. As the speed of the drive increases, the viscous friction torque also linearly increases. Third type of torque is Coulomb torque, TC, which is constant. I can show TC like this. This is TC and this is TC. So therefore all the components of friction torque are depicted in this torque speed characteristics. This is the static friction torque TS, this is the Coulomb torque TC, and this is the viscous friction torque TV, okay, in first quadrant as well as in third quadrant. Now if you add up all these, what is the total friction torque? It is the sum of the three. If you add up all these, so it will become like this. Let me show it here. This is the friction torque, speed. It will become something like this. Similarly, something like this. When the motor and its driven load, I mean when the drive is at standstill, it's not running, then it has a certain amount of friction torque, which is, again, I call it static torque or stiction. So at standstill, a large amount of torque is to be developed by motor to overcome this friction torque. And then as motor accelerates, you can see this static friction torque decreases, and then it linearly increases with speed in first quadrant as well as in third quadrant. Okay, so this is about various components of friction torque, and when we add up all these components, we get the friction torque, total friction torque TF, like this. This is the total friction torque in the first quadrant and in the third quadrant. Now what we can do, we can add windage torque also, because if you remember just few moments back, I told you that total torque is the useful torque TL plus friction torque, which has all these components, plus windage torque. As far as this windage torque is concerned, what is windage torque? Windage torque is the torque because of opposing torque, of course, because of air resistance. See, when the motor runs and its driven load runs, it runs against the air resistance. It hits the air. There is air in the opposite direction, and that air resistance always opposes the motion of the motor and its driven load. And the torque, opposing torque, because of the air resistance, that's called windage torque. And that windage torque is not constant. It is directly proportional to square of the speed. As the speed increases, the windage torque increases as square of the speed. So TW we can write as a constant K into omega m square. If you show that windage torque also in this characteristic, windage torque I can show by this dotted curve. So this is windage torque TW in first quadrant and it is in third quadrant. Now if you add up all these torques, you will get the total. You add the load torque plus friction torque plus windage torque. So the total torque becomes like this. This is the total load torque TL minus TL omega m minus omega m. So it becomes something like this. This is the total load torque TL in first quadrant and in third quadrant. Of course, it is the summation of load torque, useful load torque, which is required to drive the load, plus friction torque, which has all these components, which I have already shown in this curve, and we have added these components, and we got something like this, if you remember, total friction torque like this, plus windage torque. When we add all these, we add these components of the friction torque with the windage torque, we get the total load torque like this. Okay. So this is about various components of load torque. Now once we have the knowledge about what are the various components of load torque required, next is that we will try to understand what are the types of useful load torques and what are the characteristics of useful load torques. I write here types and characteristics of useful load torques. One of the very important components of load torques is the useful load torque. What are the various types of loads? See, all the loads do not have similar type or same type of load characteristics, torque speed characteristics. Different loads exhibit different types of speed torque characteristics. Let us consider a few loads, very important loads, which are general loads. Our in our day-to-day applications we use these loads and see their characteristics. The first type of load is fan type load, blower type load, centrifugal pump, or I can write pump type of load, and compressor type of load. Compressor type of loads. So this is one category of loads, very common in our households and also in industries. Fan load, blower load, pump load, and compressor load. And in these loads, the useful load torque is directly proportional to square of the speed. The load torque is not constant. The load torque varies with the square of the speed. So the torque speed characteristics of these types of loads are like this. So this is the load torque TL versus speed, and this is the when you plot this, it is something like this. So this is the load torque characteristic. You can see the torque is proportional to square of. It's not a linear relationship. It's a non-linear relationship. Torque is not proportional to speed. It's proportional to square of the speed. So we get this type of load torque characteristic for fan type load, blower type load, pump type load, or compressor type of load. Fine. So therefore, whenever you have to select a motor for driving this type of load, say fan or blower or pump or compressor type of load, whose load torque characteristics, speed torque characteristics are like this. So it will help you in the selection of proper type of drive or proper motor for driving or for running this type of load. Okay, so this is one category of load. Second category of load is crane and hoist load. Crane and hoist. The job of hoist or crane is to lift the objects from through certain height, okay, from ground floor to certain height. And these types of loads, crane load or hoist type of load, has this type of torque speed characteristics. Let me show torque speed characteristics. This is the torque, load torque versus speed. and this is minus omega m. So it has constant torque as far as low speed cranes or low speed hoists are concerned. But for high speed cranes or high speed hoists, the characteristics are given by this dashed line. So this is for low speed operation, low speeds, and this characteristic is for high speeds. Actually, what does a crane do? This is what a crane does. This is the object, it has to lift this object. So it lifts against the force of gravity. If the crane or hoist lifts this object against the force of gravity at a small speed, it has to work against the force of gravity. So therefore, what is the type of torque? It has to develop a constant torque. So torque is constant. But if this hoist or crane lifts the object very quickly at a high speed, okay, then it has to face the windage also, air resistance. Okay, because of the air resistance, we know that the torque does not remain constant. It has to develop a torque against the force of gravity, which is constant torque, plus it has to develop the torque against the air resistance, which is not constant, which is proportional to square of the speed. So that's why this characteristic for high speeds, the torque is not constant. The torque varies like this. For low speed cranes or low speed hoists, the torque is constant. Okay, and it is dictated only by the force of gravity. But for high speed cranes or high speed hoists, the torque is not constant. It varies like this. So this is second type of load. Third type of load is electric traction. Electric traction. When I say electric traction, in the broad sense means electric vehicle, EV, and locomotive of a train, electric locomotive of a train. We already know that there is the modern trend towards going for the use of electric vehicles. Electric vehicles also use electric drives for running the vehicle. Similarly, locomotives in electric traction. In electric railways, we use electric traction or locomotives, which are driven by the motors. So we have electric drives in both the cases. And the electric traction type of load, whether it's electric vehicle or locomotive, the load torque characteristics are like this. So this is load torque versus speed. Torque speed characteristics are like this. Sorry, let me correct it. These are the torque speed characteristics. Initially, when the train or when the vehicle is at no load, it requires large starting torque, because if you take a train has very large friction torque at the beginning. Its stiction or static torque is very static friction torque is very large. Okay, and then the motor has to develop a very large starting torque, and once the motor runs, then this torque requirement reduces, and then it becomes almost linear like this. So that means for electric vehicles and for electric locomotives, electric trains, especially for electric trains, large starting torque is required, because the train has to be started against a large frictional torque. So then this is the torque speed characteristic for electric traction type of load. And finally, we have constant power loads. Let me give the example of constant power load. Constant power load. One of the example of constant power load is, if I write example, is coil winder. Coil winder. The job of coil winder is to roll the cloth around a pulley, a sort of pulley. It's something like this. You see, this is the pulley, this is the radius of pulley, and the pulley rotates at a speed omega m. It is driven by a motor, and this is the belt which rotates or which moves at a velocity v, and the tractive force developed is Ft. Okay. Now what is the speed? The job of this is this may be the cloth, to roll the cloth around this coil. Okay, this is called coil winder. The job is to roll the cloth, to wind the cloth. The speed omega m is given by V by R, where V is the velocity and R is the radius of this pulley, right? So from this, V is equal to omega m into R. What is power developed by this drive? Power P is equal to, it is given by force Ft into velocity. This is the definition of power. And what is, if I write Ft into velocity, velocity is given by omega m into R. So P is equal to, if I write like this, if I write Ft into R multiplied by omega m. What is force into radius? That's nothing but torque. F into R is torque, that is T into omega m. And this power remains constant in these types of drives. So in constant power load, like example is coil winder, okay, this is the operation. Operation takes place like this. The cloth is wound like this around this pulley or around this coil, but the power all the time remains constant. That means if the coil winder runs at a high speed, the torque requirement automatically decreases, so that T into omega m is constant. If the speed decreases, torque increases, so that power remains constant. And its torque speed characteristics are something like this. Let me show you the torque speed characteristics. This is torque and this is the speed. Torque speed characteristics are like this. You can see at low speeds, torque is high. As speed increases, torque decreases, so that P equal to omega m into T is always constant. Because one parameter increases, the other parameter decreases, and vice versa. Power remains always constant. So, I mean, this is another example of a load and torque speed characteristics of constant power load. The torque speed characteristics of constant power load are like this. And finally, I will take one more example of an excavator. What is an excavator? The job of an excavator is to dig the earth. To dig the earth. It's required for digging the earth. When it digs, you may dig the earth with the help of an excavator, and the excavator may develop a large amount of torque. While digging the earth, it may happen that it may strike some stone inside the earth. And if the torque developed by the excavator is large and it strikes the stone, and the excavator may get damaged. So therefore, when it strikes the stone, the torque developed by the motor should automatically reduce, so that the excavator is not damaged. So therefore, it should have these types of torque speed characteristics. This is the load torque and this is the speed omega m. It should have this type of characteristic. This is A, B, C. This is A dash, B dash. You see initially the torque developed is this. As the speed increases, you see torque decreases. It does not remain constant. And it protects the excavator against damage when during the digging process it strikes a stone, a hard stone. So therefore, as the speed increases, the torque should decrease like this. This may be for one excavator, this may be the characteristic for another excavator, or at different speed levels. Okay, so these are the torque speed characteristics and type of load, or as for torque speed characteristics for different types of loads. We have taken different types of loads, like we have taken fan type, blower type, pump type, or compressor type load, and we have seen what are its torque speed characteristics like. We have considered crane and hoist type of load, electric traction, constant power load, and excavator type of load. And once we know the torque speed characteristics and torque requirements of these types of loads, it will help us in a long way in selecting a proper drive, a proper motor for running these types of loads. We will continue our discussions and we will see how to select a motor and how to produce a stable operation of the drive, considering these torque speed characteristics of different types of loads in the next lecture. Thank you.